Okay, so we just finished uh, conductivity, thermal conductivity, and now we're going to be doing electrical conductivity, which includes electrical properties, resistivity, and conductivity. So, resistivity is a quantified measure of a material's ability to resist electrical current. So, a low resistivity value means that the material is a good conductor and not a good insulator. To calculate resistivity, use the formula PEI is the resistivity of the material. R is the electrical resistance of a uniform specimen of a material. I is the length of the sample. And A, of course, is the cross-sectional area of that sample. So we measure resistivity in units of ohm meters. Ohm meters. Do not confuse electrical resistivity, which is a property of a material, with the electrical resistance R of a component. The resistance R of a component is different. That's part of a circuit. All right, so conductivity is a measure of how well materials conducts electricity. This property is useful in designs requiring the transmission of an electrical signal. To calculate conductivity, find the reciprocal of resistivity, which is 1 divided by the resistivity. Okay, and then we measure conductivity in units of Siemens per meter or S per M. Now, investigate the electrical conductivity of 6 material samples. Each material sample is a cylindrical rod with a diameter of 1/4 inch and a length of 4 inches. Okay, so it's a 1/4 inch diameter rod and it's 4 inches long. We have A, B, C, D, E, and F. Similarly, as we did with with density, elasticity, thermal conductivity, and now electrical conductivity. And then the next thing we're going to be doing is hardness. Then we're going to be able to go in and totally complete the chart on 2.3.1 where we can add all the properties of these materials. So here it says, review the 3 elements of electrical circuits, series and parallel circuits, and electrical circuit measurements and calculations section of the electricity resource. So we're going to bounce over to there because it's important that we know this first. So electricity is a form of energy that results from the flow of charged particles, including protons and electrons. This electrical energy can be stored, transmitted, and converted efficiently into other forms of energy that are useful to us, such as light, heat, sound, and motion. All right, so power systems. Electrical power is transported and consumed in 2 main forms: alternating current, which is AC, and direct current, which is DC. Put them together and you get the band AC/DC. Or, okay, forget about it. Anyway, so AC power is transported from a power generating plant by high voltage power lines to your house. And then it's converted into useful forms of energy, such as light through a light bulb or electricity through a wall socket to power your electronic devices. For an electrical device to operate AC power from a wall socket, another conversion needs to happen. Most electronic devices like a kitchen appliance or television only function with DC power. AC power from the wall outlet must be converted into DC power within the device, or DC power must come from a battery. For an overview of the national power system that supplies power for your homes and business, watch our energy video about the power system. Okay, So we'll do that. Um, we'll do that later. So now we have the elements of an electrical system is the system that facilitates the flow of an electrical charge to the conversion of energy is an electrical circuit. All right. So the flow of an electrical charge is supplied typically by a battery for the national power system that was described in the previous section. So electrical circuits can be very simple or they can be quite complex, but every circuit needs at least three elements to function. And that is a source to supply the electrical energy, a load to consume electrical energy, and a conductive path to form a continuous path for the source, from the source to the load, right? So we want to have that source of energy. We need to have a load, and then we need to have the path. As an example, of an electrical circuit, Figure 1 shows a battery as the source of electrical energy. Electrically conductive wires transport the energy to the light bulb, where the energy is converted into light energy, as you can see, okay? There's our source, there's our conductors, and there's our load. Okay, so remember, you have to be able to go back. You need to complete the circuit in order to do that. So an incandescent light bulb is a device that converts electrical energy into light and thermal energy. The thermal energy makes the light become hot and wastes electrical energy, right? Because as that light bulb gets bright, it also gets very hot, which in turn means that energy is being emitted through that heat. So a light emitting diode, LED, y'all know what the LEDs are, operates differently from an incandescent bulb in that electrical energy is converted into light and very few other forms of energy, which is why you have less energy loss through that. Okay, because it turns it into light and no other form of energy, so you don't get that heat, so you don't get that energy loss. All right, the energy conversion is so efficient that a resistor is needed to absorb some of the energy to avoid a short circuit. So this is where we have the resistors, not resistivity. Now we have resistors, and the resistors, they are needed to absorb, right? We have resistors that absorb some of the energy so we don't short circuit or we don't overload the device that we are trying to power. This efficient conversion, is what makes LEDs so much more efficient than an incandescent light bulb, and it's why homes across the United States are converting from incandescent to LED. It makes total sense because number one, it's going to last longer because you're not getting energy loss through heat, right? It is efficiently converting that energy into light. So here we have a circuit schematic, and get used to it because this is what it's going to be like quite a bit. To efficiently represent a circuit design, a graphical model called a circuit schematic is used instead of drawing realistic images representation of each component. The schematic represents the circuit, electrical path, and components with lines for wires and standard symbols. So figure 3 is a circuit schematic of the electrical circuit shown in figure 1. So here, that is actually this, okay? This is shown here as it will be all the time. There's the schematic. So we have a 9-volt battery, and then there's the circuit, there's the light, and it goes right back in to the into the battery. And here we have a ground that keeps everything copacetic. All right. So this is what an LED looks like. This is the power supply, right? That's a battery. And then a resistor looks like that. And a resistor is measured in ohms, okay? In ohms. Or you might see kilo ohms, okay, if it's thousands. All right. And then we have amp meters and voltmeters. And which I have right here, and which we'll be using to measure some of this jazz. Okay. So here's the difference between a series circuit is one that has only one path for a circuit for current. That's in figure 5. And a parallel circuit has more than one path. All right. It is, here you can see that here we have our battery and the voltage. I is current. I is for current, right? So you see that our current flows here. Here we have resistor 1, volt 1, volt 2, volt 3, and resistor 3. So a more complex electrical circuit is a combination circuit. That's in which components are connected as series and parallel configurations as shown in figure 7. So here we have again our current going into the resistor 1. We have voltage 1. The voltage drops as the current flows through the resistor, and so on. All right. So again, and then we have our ground here. So electrical energy has 3 fundamental properties. So we have current, voltage, and resistance. Okay, current, voltage, and resistance. And the symbol for voltage, the unit is volts, and the symbol is V. Current is I. I know it doesn't make sense, but that's what it is. And the units is amperes and or amps, and the symbol is A. Resistance is measured in ohms, and it is omega. Okay, so these are the important things to know. So voltage is equal to current times resistance. Ohm's law is the mathematical relationship between current, voltage, and resistance. The current through a load and the resistance of a load both vary in direct proportion. The voltage applied to the circuit is shown in the Ohm's law formula. So here we have, this is a series circuit. A flashlight uses a 6-volt battery and has a bulb with a resistance of 150 ohms, as shown in figure 8. Okay. When the flashlight is powered on, you can calculate the current flowing from the battery. So our voltage is 6 volts and our resistance is 150 ohms. So now we just rearrange this formula from V equals IR to I equals V divided by R, and we come up with 6 volts divided by 150 ohms gives us a current of 0.04 amps or 40 milliamps, okay? 40 milliamps. So very important to understand the conversion in units for this. All right, now we start to get into a little more heavy-duty detail, and this is Kirchhoff's laws. And Kirchhoff, the laws are named after he was a physicist who first described them. and their mathematical relationships. There we go again. I told you, you're going to be mathematical wizards when you get through with this class. So Kirchhoff's voltage law is KVL, okay, states that the algebraic sum of all voltage around any closed path must equal 0, okay? The algebraic sum of all voltages around any closed path must equal 0. That's Kirchhoff's voltage law. Kirchhoff's current law states that the algebraic sum of all currents into and out of any branch in a circuit must equal 0. The algebraic sum of all currents into and out of any branch must equal 0. So, so this table shows an overview of how Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law are applied to series and parallel. Okay, so here we have, on one side we have series circuits, and the other is parallel circuits. So the resistance in a series circuit, the total resistance is equal to the sum of the resistance of each component. Example, R1 plus R2 plus R3 and so on is equal to the total resistance, or RT. In a parallel circuit, the total resistance is equal to the reciprocal of the sum of the reciprocal resistance of each component. Yeah, is that weird? That's weird. So in order to get the total resistance, you're going to add up the reciprocals of each of the resistors. So it'd be 1 divided by resistance 1 plus 1 divided by resistance 2 plus 1 divided by resistor 3, and so on. And then we take 1 divided by that, and we come up with the total resistance. Okay? I know it looks funky, but that's the way it is. Not a big deal. All right. Kirchhoff's voltage law says that the voltage supplied by the source, VT, is equal to the sum of the voltage loss across each component. All right. So the total voltage is equal to the sum of the voltage loss across each circuit. Therefore, right, because as it's going through a component or a resistor, you're going to have a voltage drop. It's just the way that it is. So, and then in a parallel circuit, the voltage supplied by the source, VT, is equal to the voltage loss across each parallel component. So there you go again. VT is equal to V1 equal to V2 equal to V, and so on. All right, that's how that goes. Okay, Kirchhoff's current law states that the current flowing from the source is equal to the flowing through that flowing through each component. So total current is equal to the current flowing through component 1, component 2. All right. In a parallel system, the current flowing from the source is equal to the sum of the current through each branch. So IT is equal to I1 plus I2 plus, all right, so you'd have to add them up in a parallel system. All right. Ohm's law states that the voltage supplied by the source, the total voltage, is equal to the product of the current and the resistance. VT equals IT times RT. Okay. And then the voltage supplied by the source in a parallel system is equal to the product of the total circuit current and total circuit resistance. All right. The voltage is equal to IT times RT. No change in that. So here's an example Use the laws of circuit theory to calculate the following: total resistance, current through each component, and voltage across each component. So here we have a series circuit with a battery of 12 volts. We have three resistors. One is 220 ohms, R2 is 470 ohms, and R3 is 1.2 kilo ohms or 1200 ohms. Okay? Don't let that confuse you. So now our total resistance, we add those up and we come up with a total resistance of 1,890 ohms. Okay? In order to find the current flowing through each component, it is I1 equals I2 equals I3. So total current is equal to the total voltage divided by the total resistance, which is 12 volts divided by 1,890 ohms. Our current total is 0.0063 amps or 6.3 milliamps. Okay, so and then here's our voltage drops across V1, V2, and V3. All right, V1 would be the current times the resistance, which would be 0.63 times 220, 0.63, because we found that right up here. All right, and you go through it, and then that should all add up to 12 volts. If it doesn't, there's a problem. Then here, we're almost done. We're almost done. Okay, for a parallel circuit, a little more complex. As you can see, their total resistance is equal to the reciprocal value of each resistor added. It's the sum of the reciprocal of the resistors. So we have 1 divided by 470 ohms plus 1 divided by 220 ohms or 2200 ohms, and 1 divided by 3300 ohms. And right, 3.3 kilo ohms is 3,300. So we do that and we come up with a sum of 0.002885. And so 1 divided by that, we come up with a 346.6 ohms total resistance. All right, now the current flowing through each component, IT, I1, I2, I3, is equal to this, where we have 15 volts divided by the total resistance. And so our total current therein is 43.2 milliamps or 0.432 amps, right? The total current is equal to the voltage divided by the total resistance. All right, and then that gives us that. And then we could find each current and make sure that it adds up by going through the steps where voltage divided by R1, where VT is equal to all these. So here we have 15 volts divided by 470 ohms. And I1, current at component 1, is 31.9. The current at component 2 is 6.8 milliamps. And the current at component 3 is 4.5 amps. And if we add those all together, we should come up with the total current that we came up with up here. All right. Now, there's a voltage across each component. So we have our voltage drops across each component, whereas V equals I times R. So if the voltage is equal to 31.9 milliamps that we found up here for component 1, and that is 1 divided by 1,000 times 470. That gives us a voltage of 15.0 volts. And across 2, it gives us 15.0 volts. And across 3, 15.0 volts. This is a circuit troubleshooting checklist, which is important to have when we're building a circuit and we are attaching these leads to find out what the volts and the amps are through a system. All right. So that is that. I wanted to make sure you have this because we're going to do the problems, but I want you to have this first off. So, and then we'll look at that together. All right. So please take these notes and try to enjoy electricity as much as you can.